Today we're going to talk about atoms, ions, and isotopes. Oh my! So here's a brief history of the atomic model through time, from Democritus, where it was just a solid ball of matter, all the way up to the current model, which is called the quantum cloud model, where we have a dense positively charged nucleus with protons and neutrons, and the electrons in a cloud all around it. The first real significant model that you're expected to know is the gold foil experiment that developed Rutherford's model. Rutherford studied the atom and came up with this model based on J.J. Thomson's plum pudding model, which showed a positively charged mass with electrons dotted throughout. So Rutherford wanted to prove that. And so he sent a positive charge, that's the alpha particles, through a piece of gold foil. Now, since the gold foil was thought to not have really any charge, but the electrons being most of what the atom was, he expected the positive charge to be directed through in a straight line and end up directly on the other side. Which, if you look here, most of the particles did go straight through. However, some of them ricocheted directly back, didn't even go through the foil at all, and some of them were veered off to the sides. So it was these that veered off to the sides and ricocheted that caused Rutherford to conclude that there must be positive charges in the atom. The atom was mostly empty space because most of them did go through, but there must be positively charged particles in the atom as well. And he called those positively charged particles protons. So by the end of Rutherford's experiment, what he concluded was, yes, the atom is mostly empty space. So no more plums in the pudding, right? Or I used to call it the chocolate chip cookie model because that's just more delicious. So for J.J. Thomson's model, if you think of a chocolate chip cookie, the cookie part is the atom, and then the chocolate chips are the electrons. So when Rutherford revised the model of the atom, he's got the atom as mostly empty space, but in the center of the atom is positively charged dense particles called and so we know those are protons in the nucleus. So Rutherford adds a positively charged nucleus to the model of the atom. J.J. Thomson added electrons. Rutherford adds a nucleus and protons. When we move to the current model, we have to talk about how the electrons are organized. Okay? Light at the time was being debated. There was one camp that said light travels in waves. Then there was another camp that said light travels as particles, so little dots of light. But what both sides concluded eventually was that yes, light is particles, but these particles actually travel in waves. It's called the dual nature of light. And if you recall from when you studied this in middle school, light has frequency and it has wavelength. Waves have frequency and wavelength. So, when we talk about frequency, we look at how many waves pass a point. So if we look at this point right here, this line, see this line right here? If we look, this top wave is going to have more waves pass than the wave on the bottom. Wavelength is the difference between two peaks or two troughs. So the distance here and the distance here. So what you see is if you have a high frequency wave, you have a short wavelength. And if you have a low frequency wave, you have a longer wavelength. So if you think of these dots traveling in waves, then that is how light travels. And so by studying this, Bohr revised the model of the atom to include what he called orbits. And so we have our electrons here, that's the green dot, traveling in an orbit around the nucleus. At this point, we do have neutrons as well in the nucleus, but neutrons have no charge, so they don't really affect how the electrons behave. They just affect the mass. So we've got protons in the nucleus with neutrons, and then the electrons in orbits. Now, these orbits have energy. And the energy increases as you get farther away. So what happens is when these atoms absorb energy, the electrons can go up to a higher energy level, so a higher orbit. However, it's not stable there. So it will eventually fall back down, and when it does, the energy will be released as light. And this is a light that has a specific wavelength and frequency. And when those wavelengths are in the visible spectrum, we see them as colors. And so that's why when you have your fireworks display and we see whites and greens and reds and blues, those are different elements that have their electrons in different energy levels. When the heat from the spark ignites them, those electrons get excited. We call it excited state. And they go to these higher orbits. They don't stay there. Those electrons then fall down to the lower orbits, emitting these photons of light that has specific wavelengths and gives us all those beautiful colors. All right. And so here we have what's called a light spectrum. The continuous spectrum looks like this, but if we isolate through a diffracting lens, then we can see specific wavelengths of light, and each element, believe it or not, has a specific wavelength of light, a specific spectrum that it will send out because its electrons get excited in a specific way. So these spectra can actually be used to identify elements. Isn't that cool? There's a very cool video on YouTube called How Neon Lights Work. I highly recommend that you Google that and watch that later on. Okay, so here's our final model of the atom. We have our nucleus. It's that little dense, tiny part in the middle with the protons and the neutrons, and then our electron cloud, which has electrons just running around, going crazy all around it. Okay, let's compare our three subatomic particles. We have our positively charged proton, which is positive and in the nucleus. The neutron, you'll notice that the protons and the neutrons have similar mass. However, the neutron has no charge, and they're both located in the nucleus. And then outside of the nucleus, in the orbitals, we have our electrons, which have relatively no mass and are negative. So the only two charged particles are our protons, which are positive, and our electrons, which are negative. Atoms are neutral. Okay, neutral. They have no charge, which means that the number of protons is equal to the number of electrons. When we lose or gain electrons, then we form ions. Okay. In the box on the periodic table, there's a whole number. That number is the atomic number and tells us the number of protons. When you find the location of the element on the periodic table and you look at the group number, the number that's in the ones place, now this is only for groups 1 and 2, and groups, sorry, writing with a mouse is a challenge, 13 through 18. Those groups, we take the number that's in the ones place, and that tells us the number of valence electrons. And I hope you recall that the valence electrons are the electrons that can be lost to form cations, which has a positive charge, and gained to form anions, which have a negative charge. That's an A. There we go. Anion. So here's some important vocabulary words. Isotopes are atoms of the same element with different numbers of neutrons. And then we have the atomic number. The symbol for atomic number is Z. That'll come up here in a bit. And that's the number of protons that are in the nucleus. And then the mass number, A, is the total of protons and neutrons in a nucleus. This number has to be given to you or calculated. Here's our periodic table. The atomic number, again, is the whole number. The average atomic mass is the decimal that's on the bottom. Okay, and we've already talked about how the valence electrons gives us the charge of the main group elements. Just a quick review. If it's in group 1, then these elements will form a +1 charge. In group 2, they will form a +2 charge. Aluminum forms a +3 charge. We skip group 14. Group 15 forms a charge of a -3. Group 16, a charge of -2. And group 17, a charge of -1. However, the mass number is different. And here's how. So here are two isotopes of chlorine. It's the same chlorine that's in our water that you put in your pool. And there are two main isotopes. Now remember, isotopes are atoms of the same element. When we say same element, we mean they have the same number of protons. So if you're looking at your periodic table and you look up chlorine, you'll see that chlorine is atomic number 17. That means that every atom of chlorine has 17 protons. This is what we call the isotope notation. You'll notice that 17 is on the bottom. That is, again, the atomic number. Up top, this number 35 is what we call the mass number. So here, chlorine 35, when we write it this way, 35, again, is the mass number. Mass number. There we go. The other isotope of chlorine is chlorine 37. So its isotope notation could look like this. Again, you'll notice that they both have 17 in this bottom location because in order to be chlorine, it has to have 17 protons. But the mass number is different. And the mass number is different because isotopes have the same number of protons but different number of neutrons. And since protons and neutrons are what have mass, they give us the mass number. So chlorine 35 has 17 protons, 18 neutrons, and because there's no charge, it also has 17 electrons. Chlorine 37, on the other hand, 17 protons, 17 electrons, but 20 neutrons. So when you take the mass number, 35, minus the atomic number, which is 17, that gives you the number of neutrons. So here's a picture of chlorine 35 and chlorine 37. You'll notice they both have 2 in the first level. They both have 2, 4, 6, 8, 2, 4, 6, 8 in the second level, and then 2, 4, 6, 7 in the outermost, 2, 4, 6, 7. So the electrons do not differentiate an isotope from another isotope. We use electrons to differentiate between atoms and ions. And so that's something to keep in mind. Atom versus ion is charge, protons and electrons. Isotope versus isotope is nucleus, protons and neutrons. We're comparing the number of neutrons. Ions, electrons, isotopes, neutrons. All right, so let's dissect this nuclear isotope notation a little bit. And you see up here, I've got the mass number. Down here, I've got my atomic number. And then up in the right-hand corner, I would have the charge. If there's nothing written there, that means you have a neutral atom, okay? If it's positive, then you'd have a positive charge there, negative if it's a negative charge. So positive or negative there, it's an ion. So when we look here, chlorine 37, this is neutral. That means that it has 17 protons and 17 electrons. And if I want to know how many neutrons, I take my mass number minus my atomic number. So 37 minus 17 gives me 20 neutrons. Now, if I had chlorine -1 with a 37 and a 17, now the difference here is there's a charge. So here I would have 17 protons, but because that charge is -1, I have 18 electrons. I started with 17 when I was neutral. Now because I have a -1 charge, that means I have one more electron. And again, the other way to do a nuclear isotope notation is to take the name of the element dash mass number. So for example, carbon 14 or carbon 12. So here's how this works. Let's do some problems so you'll know how to do this when you look at your homework or your classwork. So here we have an element Y. Element Y is yttrium, and when we find yttrium on the periodic table, its atomic number is 39. I'm going to skip over because the atomic number is 39. The atomic number is protons, so that means it has 39 protons. I look here, there's no charge. The charge is 0, so that means it also has 39 electrons. Because if an atom is neutral, the protons are equal to the electrons. So now let's look at the mass number. The mass number is this number up top, so that would be 90. So how do I get neutrons? Neutrons, you take the mass number minus the atomic number. So we take the mass number, which is 90, minus the atomic number, which is 39. And when we take 90 minus 39, we get 51. All right, so let's look at the next one. We have fluorine. There's a -1 here. That means that it's going to have one more electron than the neutral atom. So the atomic number for fluorine is 9. That's what's at the bottom, which means it has 9 protons. That -1 means that it doesn't have 9 electrons. It has 10 electrons. The mass number written up top is 19. So when I go for neutrons, I take the mass number, 19, minus the atomic number of 9, and that gives me 10 neutrons. I'm going to skip chlorine 37 because we used him as an example earlier, and skip down here to iron, +3. Okay, iron, they did not give me the atomic number, which means I have to look at my periodic table. The atomic number for iron is 26. The mass number for this isotope is 54. All right, so the number of protons, the atomic number is 26, so it has 26 protons. When I need to get neutrons, I take the mass number, which is 54, minus the atomic number, which is 26, and that gives me 28 for the neutrons. So then I get to electrons. The electrons here are determined because I have a charge, so I have to do math. If there's no charge, then it's however many protons, I have electrons. +3 means that I've lost 3 electrons. So it started with 26, it lost 3, 26 minus 3 is 23. This next one is interesting because there's no symbol, but they did give me the atomic number. So my atomic number is 13. My mass number is 28. So I have 13 protons. There's no charge, so I have 13 electrons. And to get neutrons, I take 28 minus 13, and I have 15. But what if I wanted to complete the symbol? How could I figure out what element this is? Oh, right. The atomic number. And since the atomic number is 13, if you look at your periodic table, aluminum is number 13. So here we're talking about aluminum. All right, so go ahead and pause the video and do the sulfur problem. All right, got it? So here we go. My atomic number is 16. My protons is 16. -2 charge means that my electrons are 18. My mass number is 30, and that means that 30 minus 16 gives me 14 neutrons. Good job. Hope you feel like you have a better overview of atoms, isotopes, and ions.